Hello students, welcome to today's video. In a previous video, we have discussed about the Gauss theorem. Now in today's video, we are just going to discuss some of the applications of Gauss law. But before going to the applications of Gauss law, let's first see what was the Gauss law. Okay. Now according to Gauss law, the electric flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. Okay. Now we are going to use this Gauss law in studying some of its applications. We are going to study the applications using 3 examples. First, we'll have to take a infinitely long straight line charge and we are going to calculate the electric field for that line charge. Okay. So first I have written the electric field due to an infinitely long straight line charge. What is the second one? We'll have to take a infinite plane sheet of charge. Okay. So here I have written the electric field due to a thin infinite plane sheet of charge. What is the third example? The third example is taking a uniformly charged shell. So I have written in the third point the field due to a uniformly charged thin spherical shell. So we are going to study the applications of Gauss law using these 3 examples. Let us now take up the first example. The first example is that we have to calculate the electric field intensity due to a straight line charge. So in this diagram, what we have considered is we have considered a line on which charge is distributed uniformly. So this is a linear charge distribution. Now we have to calculate the electric field intensity due to this line charge. Okay. At what point we are going to calculate the electric field intensity? At this point, which is at a distance r. This point is considered to be P. So we are going to calculate the electric field intensity due to this straight line charge at this point, which is at a distance r, small r, from the line charge. Okay. So what we have done here is, first of all, we will just consider a cylinder of radius r. Okay. We are going to consider a cylinder of radius r. Okay, which is around this line charge. So basically what we are going to do is we have to calculate the electric flux associated with this surface. This is a flat surface. As you already know that a cylinder has 2 flat surfaces and 1 curved surface. So these 2 are the flat surfaces and this middle portion is the curved surface. So we are basically going to calculate the electric flux for this surface. Secondly, for this surface also. Then thirdly, we are going to calculate the electric flux linked with this surface. Now if we get the electric flux linked with this surface, okay, for this diagram, then what we can do, we can just equate the value of electric flux, which is phi E, with the Gauss's law. According to Gauss law, we know that phi E is equal to Q by epsilon naught. Okay, so what we calculate in Gauss law is the electric flux. Similarly, here also we are going to calculate the electric flux due to this linear charge distribution. If we then equate this value of electric flux for this whole surface with the Gauss law, then you will see that we can easily calculate the electric field intensity due to this line charge. Okay, so what we are going to consider is basically a point P, which is at a distance smaller from the line charge. Next, we consider a cylinder of radius r and whose length is L. The length of the cylinder is L. So we consider a cylinder of radius r and length L around the line charge. Okay. So here what we have done is we have put the line charge along the direction or at the place of the axis of the cylinder, not anywhere else. Okay. We consider the line charge to be along the axis of this cylinder. And now, as you already know that for a line charge, the direction of the electric field is normally outwards. So if this is a line charge, where the positive charges are uniformly distributed over the line, then the direction for the electric field for this line charge will be perpendicular or normal to this surface and outwards. Okay, so for this line charge we have the electric field along these directions. Okay, for what will be the direction of the electric field for this diagram? See, here we have considered the line charge. So in which direction will the electric field be? The electric field will be along this direction, which is normally or perpendicularly outwards. So if this is the line charge, then the direction of the electric field will be along this direction. So we have considered the electric field to be along this direction. Now let us see the area vectors. We considered the flat surface area here. For this surface area, what will be the direction of the area vector the area vector will be along this direction, which is perpendicular to the surface or normal to the surface. So we have written a unit vector for the area. Similarly, for this flat surface, for the second flat surface, the direction of the area vector will be along this direction. Okay, for what will be the direction of the area vector for this middle portion or the curved surface of the cylinder? For this curved surface, what we know is that for a cylinder or for a spherical surface, the direction of the area vector is always perpendicular to that surface at that point. Okay, so if we consider a point here, then at that point, what will be the direction of the area vector? The direction of the area vector will be perpendicular to this surface or normal to this surface. So we have written unit vector n cap along this direction. Similarly, at this point, if we consider the area vector will be perpendicular to this surface. Similarly, if we consider the bottom part, then in the bottom part we have the unit vector n cap along this direction, and similarly at this point also the unit vector will be along this direction. This is the area vector. So these are the directions of the area vectors. For these surfaces we have perpendicular vectors. So this is the area vector. For this surface, this is the area vector. For this curved surface, the area vectors are normally outwards. Now, what is the angle between the electric field and the area vectors on the different surfaces? We have considered here three surfaces. So what is the angle between the electric field E and the area vectors? See, for this surface, the electric field is along this direction and the area vector is along this direction. So for this flat surface, the angle between the electric field and the area vector is 90 degree. Similarly, for this surface, for this flat surface, the direction of electric field is along this direction and the direction of the area vector is along this direction. So they are mutually perpendicular. Okay, the angle between these two vectors is 90 degree. What is the direction, what is the angle between the electric field and the area vector for this surface? See, if we consider the electric field at this point, then that electric field would be along this direction. We haven't calculated the intensity yet, but we already know the direction. Okay, so the direction of electric field at this point will be along this direction, which is normally outwards. Similarly, the area vector, which is ds, I have considered a small area element ds here. This is a small area element ds. Now the direction of this area element or the area vector for this area element will be perpendicular to the surface. So what we see here is that the direction of E and the direction of ds is same. So the direction of E is perpendicularly upwards, okay, or normally upwards. Similarly, for the area element, we have the area vector to be along this direction. So this is E and this is vector ds. What we see, the angle between these two vectors is 0 degree. So for using those values for the angles, we have to calculate the electric flux for these three surfaces. Let us now calculate the electric flux due to the three surfaces. First of all, let's calculate the electric flux due to the curved surface. We have to calculate the electric flux linked with the curved surface, which is this part. For this part, what is the angle between the electric field and the area vector? They have already shown that the direction of electric field is along this direction and the direction of the area vector ds is also along the same direction. So what will be the angle between those two vectors? The angle will be 0 degree. Okay, so theta will become 0 degree in this case. Now what is the electric flux linked with the curved surface? Here C, for C I have written the curved surface. Okay, here C denotes the curved surface. So what is the electric flux linked with the curved surface? That will be equal to closed surface integral of E dot ds. Okay, this was the formula for electric flux. We have already studied about this in the previous videos. So what is the electric flux linked with this curved surface? That we have to integrate E dot ds for this whole curved surface, which is a closed surface. Okay, so what we have done here is we have just taken closed surface integral of E dot ds. What is E dot ds? E dot ds is nothing but E ds cos of theta, right? In this case, theta is 0 degree, so cos of 0 will become 1. So what we have is integration, closed surface integration of E dot ds. If the electric field, we have the electric field for this line charge to be constant. Okay, the electric field is constant for this whole line charge. So what we can write is the electric field to be constant. So I have kept E outside and we are going to integrate ds for the closed surface. So if we integrate ds for this whole curved surface, then what do we get? You already know that the area of this curved surface for a cylinder is twice pi RL. Okay, so if we are going to integrate a small area element ds for this whole part, if we are going to integrate a small area element ds for this whole part, then what we are going to get? We are going to get the surface area for this whole curved surface up till here. From here up till here, we are going to get the area of this part. Okay, so for that part, what is the area? It is twice pi RL. So what we get for the curved surface? The electric flux for the curved surface is E into twice pi RL. Next, we will calculate the electric flux linked with the two flat surfaces. So here we have one flat surface and here there is another flat surface. What is the angle between the electric field and the area vector for these two surfaces? As we have already seen that the direction between the electric field and the area vector for this surface is 90 degree. Similarly, for this surface also, the angle between E and ds is 90 degree. So E and ds are perpendicular to each other. So what we have here is theta is equal to 90 degree. So what will be the electric flux linked with these two surfaces? The electric flux will be closed surface integral E dot ds. Okay, for these two surfaces we are integrating E dot ds, right? So what we get here is E ds cos of 90 degree. Since theta is 90 degree, so what we get here is E ds cos 90 degree. What is the value of cos 90 degree? It's 0. So what we get here is phi f, which is the electric flux linked with the flat surfaces, to be 0. We have calculated the electric flux due to all these three surfaces. So finally what we are going to do, we are just going to calculate the total electric flux linked with the whole cylinder. Okay. Now what will be the total electric flux linked with the whole cylinder? That will be equal to the electric flux linked with the first flat surface plus the electric flux linked with this curved surface plus the electric flux linked with this flat surface. So what we are going to do, we are just going to add the electric flux due to these three surfaces, and what we are going to get? We are going to get the total electric flux linked with the cylinder. That is, the total electric flux linked with the cylinder is phi E, that is equal to phi C, which is for the curved surface, plus phi F, first flat surface, and plus phi F, that is the second flat surface. What we got the value for flux for the curved surface, that is E into twice pi RL. Okay. For phi F we have 0, and for the second flat surface we have 0. So what is the total electric flux linked with this whole cylinder? That is equal to E into twice pi RL. Now we are going to equate this value of electric flux with the Gauss law. Since in Gauss law, what do we calculate? We just calculate the electric flux linked with a closed surface. So here this cylinder is a closed surface. For this closed surface, what we get? We get the electric flux. We can equate this value of electric flux with the Gauss law. Okay. Now after that we can easily calculate the electric field due to this line charge from that equation. Now according to Gauss law, the electric flux linked with a closed surface is equal to Q by epsilon naught. Okay. So what we have got for this cylinder, the electric flux to be E into twice pi RL, that will be equal to Q by epsilon naught. From here we can easily calculate E, that is the electric field, and this will become Q by, transfer this part to this side, cross multiply. So what we get? Q by twice pi epsilon naught R into L. Now here Q by L, what is Q by L? Q by L is the linear charge density, that is equal to lambda. So I have put here lambda in place of Q by L. What we finally get is E equal to lambda by twice pi epsilon naught R. This is the value of electric field due to this line charge. What we see here is E is inversely proportional to R. Okay, it depends inversely on R. So what we have finally found out is the electric field intensity due to a straight line charge. Okay, this topic is very important from the examination point of view. Please study it properly. Thank you.